Hi, I am Muhammad Affam, a final year undergraduate at University of Moratuwa, Sri Lanka. I'll be presenting our work on cross-point, self-supervised cross-model contrastive learning for 3D point cloud understanding. This is a joint work done along with Isuru Disanayaka, Diniti Disanayaka, Amaya Dharmasri, Kanchana Tilakaratna, and Ranga Rodrigo. In this work, we are trying to investigate the following problems. Firstly, deep learning models usually require a large amount of label data to generalize and perform well in an unseen environment. However, annotating large amounts of data is often laborious and expensive. We investigate the possibility of creating a strong 3D encoder which can learn and generalize with a limited number of 3D data. With the advancements in 3D sensing technology, which facilitates extensive collection of 3D point cloud samples, we explore how those large-scale unlabeled data can be utilized to learn rich 3D representations. We also investigate the possibility of mapping the visual concepts between 3D objects and corresponding 2D images in a deep learning model. The major motivation of our work comes from human learning, where humans are inherently capable of mapping the visual concepts from 3D environment to 2D images. The proposed deep learning model should have a strong 3D encoder which can convert the 3D objects to meaningful representations in the feature space. While training, we don't utilize any of the annotated data, thus our method is a self-supervised learning approach. Specifically, we establish a correspondence between the 3D objects and the corresponding 2D images, leveraging a joint contrastive learning objective. We aim to encourage the features of 3D point clouds and that of the corresponding 2D images embedded close to each other in the feature space, while the features of other objects or images to be embedded far away from each other. We name our approach cross-point, and the diagram in the left shows the detailed architecture of it. Our model comprises of a join of a point cloud feature extractor and an image feature extractor to encode both the 3D point clouds and 2D images respectively. We use projection heads to encode both the modalities to make the feature vectors compatible in dimensionalities. Cross-point ensembles both intra-model and cross-model learning objectives. The two augmented versions of the point clouds are fed to the point cloud feature extractor with shared weights, and the 2D images, which are rendered from a random camera viewpoint of the 3D object, are fed to the image feature extractor. Cross-point has two learning objectives, namely intra-model instance discrimination and cross-model instance discrimination. The goal of IMID is to encode 3D point cloud features in the feature space, imposing invariance to augmentations. CMID learning objective is responsible for establishing the correspondence between the features of 3D objects and 2D images. We evaluate our approach across numerous downstream tasks in 3D representation learning. After training the model, we use the point cloud feature extractor to perform all the downstream tasks, and we discard all the other components. For 3D object classification, we fit a linear support vector machine on the features obtained for the training data of ModelNet 40 and evaluate it on the test set. For the 3D object part segmentation, we fine-tune the trained cross-point model on the ShapeNet part dataset. Cross-point outperforms the existing self-supervised learning approaches in both object classification and part segmentation. To validate the generalizability of our approach, we also experiment with Scan Object Tenant, which is a real-world dataset with scans of 3D objects. Crosspoint is able to generalize to real-world data distribution and achieve state-of-the-art performance in both standard 3D object classification and few-shot object classification. We also perform extensive ablation experiments to analyze the component-wise contribution in the crosspoint architecture. Our analysis shows that the proposed joint learning objective yields better performance than the individual learning objectives, and the self-supervisedly learned features inherently possess class discriminative capability. Our code and pre-trained models are available online. Feel free to use the code to reproduce our results.